Hey, astronomy class. We're going to continue that stellar evolution diagram today. So I just want to get straight to it so we don't have to waste any time. Okay. Let me show you what we got so far here. Where that? So, okay. It's kind of, we started with this sequence where we talked about how all stars live, right, through the main sequence, pretty much the same way, though in different amounts of time. And eventually their source of fuel runs out, the hydrogen, which then begins this red giant phase, right, where all stars become a red giant, we think. And at that point, they're fusing helium into carbon. After helium runs out, what happens then? Well, low mass stars, we talked about how it basically doesn't have the ability to fuse anymore, so it eventually becomes a black dwarf over time. Okay. So what I want to do today is I want to talk about, okay, what's going on with that other side there? What happens if they have more than 8 times the solar mass? Okay, so what happens if it's a high mass star? Okay, well, if it's a high mass star, it is going to fuse all elements up to number 26 on the periodic table, iron, which of course is Fe, if you guys remember chemistry class, right? So basically, in the core of these high mass stars, all of the really heavy, all of the lighter elements on the periodic table from 1 through 26 are pretty much forged in the core of the stars, these high mass stars. But once iron gets in the core, that's a problem because iron actually takes energy in, right? And as a result, it actually helps gravity collapse the core, which causes the core collapse, which causes basically all the remaining neutrons that exist in that tremendously dense core to smack into each other. And that creates what's called neutron degeneracy pressure, where no two neutrons want to occupy the same place at the same time. So they hit each other and they bounce off, creating a rebound. Okay, that rebound releases all of the stored energy in that, and that's not all, but they releases a tremendous amount of the stored energy in the core of that high mass star. That's a supernova. Okay, during a supernova explosion, all of the remaining elements on the periodic table and all the isotopes of those remaining atoms, all the radioactive isotopes that we could use for radioactive age dating, all of that is forged in the supernova explosion. And I'm going to add that because I failed to do that in the last video. All right, I'm going to say this supernova forms all remaining elements. So folks, the fact that you and I exist, we are the product of not one supernova, but probably thousands of supernova that have had really large stars that have lived and died and lived and died over and over and over again. And every time it lives and dies and lives and dies, it produces heavier elements, right? Carbon, oxygen, right? The iron in our blood only forms that fraction of a second before a star blows up in a supernova explosion. That's unbelievable, right? The gold on my finger here only forms during a supernova explosion. So the fact that there is enough gold right here on my ring finger suggests that we are the product of many, many supernova that have occurred right here in our portion of the universe. Anyways, I think I hit that part home. After the supernova, what happens? Well, we have our next fork in the road. All right, we're going to have another arrow going over like this, and another arrow going over like this. All right, perfect. So here's what happens. The supernova explosion, all of the outer layers of the star and much of the energy from the core are released out into the universe. But some of the matter, some of the core itself is actually retained by gravity. And depending on how much is retained is what gives you your fork in the road here. All right. Now, out of 10,000 supernova explosions, 9,999 of them are going to go to the left of the fork, right? And what happens is you have a star that is basically 1 solar mass to 3 solar masses in mass. Anything you have, any star that remains with 1 to 3 solar masses, right? So 1 times the mass of the sun, so basically the mass of the sun, or 3 times the mass of the sun, they end up becoming what's called a neutron star, where literally the density is so great and the gravity is so great that all that exists are neutrons. And that same pressure we talked about before, neutron degeneracy pressure, the fact that no 2 neutrons want to occupy the same space is what keeps the neutron star from collapsing, right? If that neutron degeneracy pressure didn't exist, then all 10,000 out of 10,000 supernova would go over to this side, where we get a black hole, which is actually one word. All right. Fixed, like I never made a mistake. Okay, black hole. So this is anytime there's greater than 3 solar masses that remain after the supernova. I am going to add right here, only 1 out of 10,000 supernova actually produce a black hole. But considering how old our universe is and how old our galaxy is, our galaxy is almost as old as the universe, almost 14 billion years old. We have had so many supernova, so many really large stars have lived and died, that there are tens of millions of black holes in our universe. Tens of millions, all right? Tens of millions of black holes just kind of roaming around our galaxy, and that's just our galaxy. Right? And the problem with black holes, can't see them, right? So it's really difficult to see them. We can detect them. There are different ways that we can detect them. But unless they're doing something to something else, to another star, maybe they're eating another star, they get too close to another star system, they're really hard to detect. So if there's one nearby, we wouldn't really necessarily know about it until we got too close to it. And when we got too close to it, we would know. That's when we would know. Some things would start falling apart in our solar system. That's a discussion for another time. Back to the neutron star, though. Neutron stars, all that exists are neutrons. And it's the neutrons that keep it from collapsing any further. That neutron degeneracy pressure stops gravity from collapsing it. Now, keep in mind, we have 1 to 3 times the mass of the sun. All of that matter is smushed down into something roughly 20 miles wide. That's as big as Detroit. Take the mass of the sun, smush it down to the size of Detroit. Keep in mind, you can fit 100 Earths across the sun. You can fit over 1 million Earths inside the sun. Now what we're doing is we're taking the mass of the sun and we are squishing it down to only 20 miles wide. The density is immense. 1 teaspoon, 1 measly little teaspoon of that neutron star would have a weight of, I wrote it down because I always screw this up, 100 million tons. That's a lot, just in case you know it. But it'll exist like that forever because the neutrons will just continue to fight gravity. And as long as that fight continues, it'll be a neutron star. One other thing that happens to it is it rotates ridiculously rapidly. It can rotate 1,000 times a second. So they rotate really, really fast, just like a figure skater pulling their arms in when they're rotating on the ice. They rotate even faster and faster and faster. So they rotate super, super fast. All right. Okay. Black holes, we're going to talk about another time. But that's it. That's pretty much the end of the stellar evolution diagram. We're going to talk about a couple things here. If you have questions about anything that we just talked about, please write them down right now and come to our live session on Thursday at 11 a.m. Okay? Hope to see you there. This has been good fun, folks. This has been fun. I like talking to myself, so this provides an interesting opportunity for me to do that. And I thank you for even pretending to listen, which I know some of you are pretending to listen, but that's okay.